Okay, so now can you see the screen?
Yes, sir. Yes, sir.
Okay, fine, that's good. So let us start. So we were looking at solution of eigenvalue problems using numerical methods, and we saw only one of them, that is power iterations. And even within the power iterations, we saw only one variation of it, which is called as direct iterations, where if you remember, it was ax equal to yk, that was the direct equation, and you started with some xk as your assumption, and then directly multiplied that a into xk equal to yk, and you got next kind of approximation, which is yk, based on yk, and then you can continue with your iterations as long as your criteria is met. So this was direct iteration. The issue with this, or I shouldn't say issue, the characteristic of this method was that it will always gravitate, the solution or the method will always gravitate towards the highest eigenvalue. So that's why using this approach you will get only the highest eigenvalue for the system defined by matrix A. Now what if I want to find out the lowest eigenvalue? This gives me only highest eigenvalue, but I want to say find out lowest eigenvalue. So based on your understanding of linear algebra, can you try to tweak this method to get something like getting the lowest eigenvalue and corresponding eigenvector? See here, A is our matrix, and corresponding to matrix A we have eigenvalues lambda 1, lambda 2, lambda up to lambda n in increasing order. So that means if we use direct method of power iteration, we will get lambda n, that is the highest eigenvalue. The problem now is I want to find out lambda 1, the lowest eigenvalue. So is there any
We can find it for 1 upon a. So 1 upon lambda 1 will be highest. So
exactly 1 upon lambda 1 will be highest, but how will you get 1 upon lambda 1?
So
you are close to the answer, but how will you get lambda 1 upon lambda 1?
So by this method only, if we use same method for 1 upon a matrix, then we can get 1 upon lambda 1. 1 upon lambda 1 is supposed to x. So we can get x, so lambda 1 will be 1 upon x.
So which matrix we need to find out for that?
So A inverse.
A inverse, yeah, exactly. See, if suppose you have A as a matrix with lambda 1, lambda 2 up to lambda n as eigenvalues in increasing order, then what will be the A inverse eigenvalues? That will be in increasing order. If I write, then it will be 1 upon lambda n, 1 upon lambda n minus 1, 1 upon lambda 2, 1 upon lambda 1 here. So 1 upon lambda n in this case will be lowest, and then highest eigenvalue will be 1 upon lambda 1, which is nothing but inverse of that is nothing but lambda 1, which is eigenvalue of A. So this gives us the lowest eigenvalue if suppose we can get A inverse and then we can use the iterative scheme to I mean power iterations to get the lowest eigenvalue. The problem here in this case is that you need to find out A inverse, and finding out A inverse is much more problematic than finding out eigenvalues. So it is never generally done this way, that is finding out A inverse and then get the highest eigenvalue from that and find out inverse of that. So even though conceptually that's okay. It is not found out this way. There is algorithm for that avoids calculation of inverse completely altogether, but in principle what is happening is this thing. Okay, so let us now go ahead with the inverse iteration method, where we will see how this lowest eigenvalue is obtained. So that is inverse iteration. This is again power iterations, but second part of that is inverse iterations. And in this case, let us see what is first the eigenvalue problem, that is Ax is equal to lambda Bx. So that's our generalized eigenvalue problem, and we are going to solve this problem using inverse iterations so that we will get the lowest eigenvalue. Okay, and to do that we need to have some iterative scheme. So iterative scheme in this case is very simple. In case of direct iterations, I will write it here in side block. In case of direct iterations, we had written something like Ax equal to y. I mean, we used k here, isn't it? It was standard eigenvalue problem, and we used Ax equal to y. So Axk equal to yk, and you started with xk something and then multiplied it, got yk, new iteration, new approximation. So this was direct iteration because you are multiplying directly a into x. In case of inverse iteration, what you do is you start with equation something like Axk equal to Bx k minus 1. Okay, so now this is our equation. From this equation we are going to kind of iterate over the this equation. Using this equation we are going to iterate and then find out what is our xk as well as eigenvalues. I have not yet told how to find out eigenvalues, but xk is nothing but the eigenvector which will successively iterate. But how will you get the eigenvalues? The eigenvalue in this particular case will be, let us say, approximation to eigenvalue is called as rho corresponding to xk is equal to, I don't know if you are aware of this notation, I will explain that, xk comma Axk over xk comma Bxk. Do you know what is this notation?
No, sir.
You don't know?
We don't know that.
This notation is used for dot product. Okay, so that means what is xk? Is it scalar, vector, matrix? What is it?
Vector.
It's a vector. What is a into xk?
A vector.
Yeah. So this xk is also a vector. A into xk is also a vector. So dot product of those two vectors is written like this: xk comma a into xk into this triangular bracket or whatever it is called. This is dot product notation. This is very standard notation. You should remember this. Okay. So this and I hope everybody knows about dot product, isn't it?
Yes, sir.
Okay, fine.
Yes, sir.
So this rho is approximation to eigenvalue. In this case, lowest eigenvalue, and xk successively is going to be approximation to eigenvector, but this xk need to be normalized so that we can get a proper I mean the xk value, the values within the xk do not blow off exponentially. So So we need to normalize it at each step, and the normalized eigenvector xk cap, let us call it xk cap, is given by 1 over xk comma bxk square root xk. So what is happening here? In this third step, you have this last step is only for normalization. You see, this is our actual vector that we have obtained. It will be normalized, that is, each value of that xk will be scaled down by a factor which is given by this square root of this dot product. Since we know that dot product of two vectors is going to be a scalar, so square root of that will be used as a scaling parameter, and then each value of xk will then be scaled by that particular scaling parameter, and then whatever xk cap we get, that is called as our new or improved eigenvector. Getting my point here? So overall, how the iterative procedure works here, what you do is you start first with some, let us say, x0. Here itself, okay, I will write here itself. So from this equation you will start. You start with some x0. Use that x0 here. Get b into x0. Now a into xk is equal to b into a into x1 is equal to b into x0. So this vector is known, right hand side is known, a is completely known, so xk is unknown. So you have to solve this equation first. Solve a into xk is equal to b into xk minus 1. You will get xk. So in this particular case, from this equation you will get x1. Use that x1, find out approximation to eigenvalue using this expression. Because all other things are known, like a is known, b is known, and xk you just have found out. And that is your first approximation. And eigenvector, to find out eigenvector, whatever xk you have, divide that by this scaling parameter. You will get xk cap. Now if you are satisfied with this answer, I mean if your answer is within whatever your error limit is, then you can stop. If not, then you can use this xk cap as your next iteration. So for your next iteration, so you can start like use this one, use it here. Understood?
Sir, can you please repeat again from step 2 to step 3? We are getting xk. This row is a function, or is it multiplied into xk?
No, it's a function of xk.
It's a function of xk. So we are getting xk from step 2 and using that xk and scaling it down in step 3.
You are getting xk in this step itself.
Okay, yeah.
Solving, isn't it? This is a function. Row. This is not multiplied. This is a function here.
Oh yes. Xk is also in step 1. Okay.
And then you get rho into xk and x cap from these two equations. Now, whether this row is sufficiently close to eigenvalue or not, I mean successively close or not. If suppose it's not, then you will choose this x cap as it is again here into your first equation. Get another xk. I mean the xk plus 1 it will be, and then continue.
Okay, sir. Okay. Understood.
Sir? Sir, this equation axk is equal to bxk. This is the equation directly given for solving this inverse iteration, right? There is no proof for it.
What proof?
We are directly using it.
This is your eigenvalue problem. So
no, sir. This next problem. Axk is equal to bxk.
Exactly. So this comes from this itself. Only lambda is not there because lambda into, this is ideal problem. Now lambda into x itself is our contains in this xk minus 1.
Okay.
Because then we see we take out lambda later on. So this equation, it's not like I am proposing something new. This equation itself is based on the first eigenvalue problem, ax equal to lambda bx.
Yes, sir.
Okay, so this is inverse iterations, and the inverse iteration, now the property of inverse iterations is that it will always gravitate towards the lowest eigenvalue. So the problem partly is solved, that is, I now have a method which can find out highest eigenvalue, I have a method which can find out lowest eigenvalue. But what if I have to find out any middle value in between them? So that is also should be possible. Of course, there are many ways of doing that. Now we will just move one step ahead and see, is there any way I can use this information or modify this to get any of the middle values in between. Okay, so to do that, the next thing actually is its inverse iteration itself, but we will modify the modified inverse iteration, we can say. We will modify the inverse iteration with a shift parameter, and surprisingly then what will happen is the shift based on the shift parameter we will gravitate towards one particular eigenvalue which will neither be highest or lowest but somewhere in between depending upon the shift parameter. So the shift parameter is used somewhere here in between, in the first equation itself, ax equal to bx k minus 1. So instead of this equation we will use a shifted equation. So that is, the shifted equation is given as a minus mu b times x, I guess, yeah, x is equal to lambda minus mu into bx. So what we are doing here is, in this case we had axk is equal to bxk minus 1. Now of course I can write this k and k minus 1 here, but the main part that I want to focus on is here. Instead of getting A matrix, we are getting A minus mu into B, and similarly instead of writing B into xk, we are writing lambda minus mu into bx. So this is our kind of shifted eigenvalue problem where mu is shift parameter. Now compare this with our generalized eigenvalue problem. Where will this what are the eigenvalues of this problem?
Sir, still lambda is still
No, it is now lambda minus mu. Isn't it?
sir, but ultimately we are supposed to find lambda only, no?
That is okay. For now, just tell me what I asked. Isn't it lambda minus mu?
Yeah, for this equation lambda minus.
Lambda minus mu is our eigenvalues, and corresponding eigenvectors will also be there, of course. So now, where will this gravitate towards, or what it will give? If I use power iterations, what it will give?
The maximum minus mu.
Correct, maximum. So if I use power iterations, direct iterations, it will it will give maximum value of lambda minus mu, isn't it? Maximum eigenvalue, isn't it? So let us call that as zk. So let us say z or z is equal to lambda minus mu. So if I use direct power iterations, I will get z value, and power iterations, direct power iterations, then z will be maximum z value. Now from this, how will I write lambda?
So z plus mu.
Yeah, z plus mu. Lambda is equal to z plus mu. Okay, no, this will not be. Okay, let us say power iteration, instead of this, power iterations inverse. What will happen if I use inverse? Then z will be minimum. So in this case, how can I get it? Z is maximum. I think I'm confused somewhere. Wait a minute. Okay, here this logic is slightly twisted. So if I use inverse power iterations, that is this inverse power iteration, then this solution to this problem will gravitate towards maximum, that is 1 over lambda minus mu maximum. Getting this point? For inverse iterations, the solution will gravitate towards maximum value of 1 upon lambda minus mu. So let us call this as zk equal to z, let us say. Getting this point?
Yes, sir.
Okay, so if this is the equation, then from this what will be lambda? right? Plus ui plus mu, isn't it? So based on this I can say lambda is equal to 1 upon z plus mu. Now let us look at initial discussion what we had again. What is mu? Mu is the shift parameter. And what is z? Z is the highest eigenvalue that we have. So if this value is too high, then 1 upon z will be very low. And mu lambda will be approximately equal to mu. Getting the point here? So in other words, what I can say is that if suppose I choose a shift parameter in between lowest and highest eigenvalue, then based upon the value of shift parameter, the solution will converge to nearest eigenvalue to this mu. So if suppose I had chosen, let us say lowest eigenvalue is 1, highest eigenvalue is 10. If I choose mu is equal to, let us say 4, then whatever nearer to 4, somewhere here let us say 5 is our another eigenvalue, then this 4, due to this shift parameter 4, the value will converge to 5, which is in between minimum and maximum. Now if suppose there are multiple eigenvalues in between here, then whichever is closer to that mu will converge to that particular value. So that is the interesting part about shift parameter. Now how to use the shift parameter and what are the ways of obtaining the shift parameter, or rather clever ways of getting the shift parameter, that's we are going to see next. But now the main important point here is that shift parameter gives us a way to identify any of the intermediate frequencies or eigenvalues and corresponding mode shape if suppose we choose shift parameter very cleverly. Okay, so how to choose the shift parameter? What are the ways of obtaining rough estimate of shift parameter? So there are two ways that we are going to see in this particular discussion. The first one is Gershgorin disks. Gershgorin disks, this is a very simple method and very effective other method if suppose your matrix is diagonally dominant, to obtain estimate of what are the eigenvalues. And it is very simple, so simple that you can do it without even pen and paper. The Gershgorin disk, if I have to write it in a expression, it says that the eigenvalue lambda will be in between aii minus summation aij j equal to 1 to n, and j is not equal to I, less than lambda less than aii plus summation j equal to 1 to n, j equal to I, sorry, j not equal to I, aij. So this mathematical expression, if you see, you may feel like, okay, what is this, what is happening over here? But it's very simple. What is aii? That's the diagonal term, isn't it? And what are aij? Of diagonal terms. This summation only indicates that j not equal to I. That means for off diagonal terms, that is j is not equal to I. So diagonal terms are here, off diagonal terms are here. So for each row, the diagonal term minus sum of off diagonal terms, and this should be in absolute terms. Okay, so diagonal term minus sum of off diagonal terms, and here diagonal term plus sum of diagonal off diagonal terms. in between these two you will have lambda, or one of the natural frequencies, square root of natural frequencies. So if suppose I take a matrix something like this, let us say 2, 0.5, 0.1, 0.7, 3.2 and 1, 0.3 and then 4, some matrix I have taken. So apply this Gershgorin disk formula to the first row. What it will give is AII, diagonal term is 2, minus sum of off diagonal terms 0.6, should be less than lambda and should be less than 2 plus 0.6, so 2.6. So here I can write 2 minus 0.6 means 1.4. Apply this to second one. It gives me 3 minus 0.9, so 2.1 lambda 3.9, and third one 4 minus 1.3, so 2.7 lambda 5.3. So Gershgorin disk tells me that the three eigenvalues of this system, the first eigenvalue or those eigenvalues will be in between these ranges. So I can use this to find out the initial approximation for our shift parameter. So this is one way of finding it out, and this is not only applicable to rows, but it is also applicable to column. You can apply it to columns as well to find out or to narrow down the range of the lambda. And now this is range, but why? Yeah.
Sir, the diagonal element will be taken with sign, or absolute value we have to take for diagonal element?
It is as it is. I have not mentioned anything over here. It is as it is.
Okay.
Okay. And I mentioned disks, but there is no disk here. Where is the disk? The disk appears only when you have complex eigenvalues. The disks are in complex plane, so this is real and imaginary axis, and if suppose there are complex values, then or even if suppose eigenvalues are complex, you will get a disk somewhere here, like middle value is here and then disk around this. So ideally your eigenvalues will be somewhere in this range for first eigenvalue. Let us say second eigenvalue, so somewhere center is centered around this and something like this. And where will be the center? The center will be this diagonal value. So 3 will be, let us say this is 3, so 3 will be my center, and radius will be given by this 0.9. Radius here will be 0.9 because 3 middle, 0.9 towards left and right. So these are nothing but radius. And within that disk itself you will have your eigenvalues. This approximation works very well for diagonally dominant matrices. If you have matrices with diagonal dominant elements, so that's what I have actually drawn here, written here, that diagonal elements are much larger than off diagonal elements. So if that is the case, then your Gershgorin disk approximation will be very close to actual eigenvalues, and it will shift from that if suppose you have very closely spaced eigenvalues and then this is not diagonally dominant and so on. Okay, so this is one way of obtaining shift parameter. There is another way, a systematic way of obtaining shift parameter, and which is important for us, and that is called as Rayleigh's quotient. And this Rayleigh's quotient gives us a very easy way of obtaining a shift parameter. So Rayleigh's quotient itself can be used as a shift parameter. So let us first discuss what is Rayleigh's quotient. Rayleigh's quotient, let us say, let us use some symbol. If suppose sir has used some symbol, I will use the same thing. Sir has used rho here. Okay, I will use mu. Rho is not a good choice, I feel, right now, because we have already used it somewhere else. So mu is the Rayleigh's quotient, let us say, or mu r, and that is given by, in our system, that is given by phi transpose k phi divided by phi transpose m phi, or if you use the generalized eigenvalue problem in the AB form, then you can write it something like this: x comma ax and dot product of x comma bx. So this is the Rayleigh's quotient. Yeah, that's it. So this Rayleigh's quotient can be used as a shift parameter in our earlier discussion that we have seen here. In case of this mu, you can use this Rayleigh's quotient, and then you can start your solution using power iterations or inverse. I think Rayleigh's quotient should be used with inverse iterations. So you can start with the inverse iterations and then get the lowest eigenvalue, then depending upon the shift parameter you can change it. Okay, now one more last thing that we will discuss here, and that is, we have now way of finding highest eigenvalue, we have a way of finding lowest eigenvalue, and if I keep on shifting the shift parameter, changing the shift parameter, I can get any one of the intermediate or any of the intermediate eigenvalues. So far that is okay. But what if I want to go systematically? Like first I want to find out first eigenvalue, then I want to find out second, then I want to find out third, then I want to find out fourth, and so on, continue finding out up to whatever the end it is. Or inverse, you can go like highest first and then next highest, then next highest, then lowest, and so on, so forth. So if you want to find out that way, then I am going to take one example of that, how to go about one by one after the other, and then there are other methods which you can explore on your own. So let us first discuss how we can move ahead from one after the other. So we have system something like this: ax is equal to lambda bx, and which has solutions, eigen values lambda 1, lambda 2, lambda 3, and so on up to lambda n. And let us say we have obtained lambda 1, whichever method doesn't matter, we have obtained lambda 1. Lambda 1 is, and corresponding eigenvector of course is obtained. Now how to obtain lambda 2, that is the question. Okay, so to do that, what we need to do is, we can again start with any of the arbitrary x. So let us start with power iterations itself. But if we start, as I told earlier, that if we start with any arbitrary x, then it will again fall back to lambda 1. It will again converge to lambda 1. But I don't want that. I want it to converge to lambda 2. So what I need to do is, from that whatever x new approximation I get, from that new approximation I have to remove all the traces of first vector. So let us say lambda 1 is obtained, and corresponding to that x1 is known. Now this one I will draw here, I will write here x1, which is eigenvector corresponding to this lambda 1. So eigenvector is also obtained. So first eigenvalue and first eigenvector is obtained. So what I will do next is, I will start with something like ax is equal to lambda bx, and trial vector choose next trial vector x0, but as I said, it will by default gravitate towards lambda 1. To avoid that, remove traces of x1, that is this, the first eigenvector from x0. How to do that? So our improved eigenvector in this case will be x is equal to x of 0 minus q. Sorry, I should have mentioned that. What are the basis vectors you are using in your discussion so far?
IJK.
Those are the generalized coordinate system, something like what sir has used a notation. I don't know actually. In modal coordinate system, what are the coordinates you are using? Q1, Q2?
Yes, sir.
Or Z1 something?
So QK, I think.
QK. So then Q you have used, I think. Okay. So in that case, what you have to do is x0 minus q1. Now this one I shouldn't say x1, then it should be q1. Q1 is our first eigenvector, then q1, and here it will be q1. Okay, so x0 minus q1 into dot product of x0 and q1. Yeah, q1 dot x0. So what is happening here? Can anyone explain by looking at the equation? What is the dot product here? What dot product this indicates?
This the part of q1 lying on x0 will be that part in the direction of q1 will be subtracted from x0.
Correct. So this is our modified kind of one. We have first eigenvalue. Now for second eigenvalue and eigenvector, we are starting with some initial guess. But from that initial guess, we want to remove traces of first eigenvector, isn't it? So to do that, we take that vector itself and take its projection on first eigenvector, that is q1, and then subtract that. This q1 gives only direction, so subtract that from initial guess, so we get a new guess, and use this x for your calculations. So this way you subtract the effect of first eigenvalue and eigenvector from your matrix and then start computation. However, of course this is technically okay, there is no problem, but this is not how we continue our calculation. Let us go one step ahead and use this information itself into our equation. So our equation was something like this: ax, where is it? Ax. So instead of this x, now substitute that a into x of 0 minus q1 into q1 dot product x of 0, isn't it? So now this one I will write something like this: a into x of 0 minus q1 transpose x0. Is this correct? Dot product can be written as q1 transpose x0, or even earlier dot products whatever we had. This one, if I have to write, I can write it as transpose of first into ax, and this part I can write transpose of first into bx. So same thing I am doing here. Q1 as it is, and Q1 dot x0 is written as transpose of first into x0. Okay, so that is the dot product. Now let us simplify this. A into take x0 common, so I minus Q1 transpose x0. Okay, so now this one I will call it as A into S1 into x0, and let us say this A into S1 is equal to some new matrix A1 x0. Okay, so this S1 is called as sweeping matrix. And if we multiply this A with S1, whatever A1 you get, this A1 has no traces of, not first, I will say lambda 1 and Q1. Okay, so as a result, whatever the new matrix A1 we have, now we can start with any x0. It doesn't matter. I need not purify it now. I need not remove the traces, because that removal of traces is carried out by sweeping matrix S1. So now this new matrix A1 will have highest or lowest, whatever, depending upon the situation, eigenvalue, but excluding the Q1 part. That is excluding the first eigenvalue that what we have obtained. So next to that, whatever it is, it will get. So A1 will have that eigenvalue now. So similarly, this is for one particular case. So if suppose you have multiple eigenvectors, so now we have obtained first eigenvector, then second eigenvector, then third one. In the third case, you need to sweep first as well as second eigenvectors, and to do that you can use sweeping matrix Sm is equal to I minus summation Qi transpose, or Qi transpose, where I is equal to 1 to m. So that means if suppose I want to obtain third eigenvalue and corresponding eigenvector, then I have to sweep first two vectors Q1 and Q2. I have to sweep out. So this will be S2. So S2 will be equal to I minus Q1 transpose minus Q2 transpose, and then you will use this S2. So you have that multiplied by S2 will give you some another vector A2, and if you use your power iteration method on this A2, then whatever Q you will get, the eigenvalue and eigenvector, that will be Q3 and corresponding eigenvalue, of course. So sweeping matrix is the matrix which kind of sweeps away the already known eigenvalues and eigenvectors. Understood?
Yes, sir.
So any query over here? Any doubts so far?
Sir, for getting lambda 3 directly, we will put m equal to 2.
Where?
Yeah, in this SM sweeping matrix for m.
For
getting lambda 3 directly, we will put m equal to 2 or 2.
M equal to 2, because we have to sweep two matrices, two Q1, isn't it? Qi's.
Yeah, lambda 1 and lambda 2. Okay.
So then you will get lambda 3 and q3.
Okay. Yes.
Sweeping matrix means it will remove remaining those parts, q1, q2. So that's why. So for that, of course, you need to know q1, q2. You cannot directly go to q3. You will first find out q1. Using that q1, you will sweep out q1, find out q2. Then using q1, q2, you will sweep out both and find out q3. Got it?
So please repeat again. Actually, my connection got broke off.
See,
After n equal to 2, yeah.
first you have A. So you will find out lambda 1 q1. Okay?
Yes.
Then you will use S1, S1, and to get S1, you need S1 is a function of, now I will write it in terms of function, S1 is a function of Q1, isn't it?
Yes, yes.
Then you will find out A1, which is equal to AS1. And
Yes.
from this this is using from this A1, you will find out lambda 2 Q2.
Yes, yes.
Then you will find out S2, which is function of Q2, and then you will find out A2 is equal to A into or A1 into S2 or A into using that expression A into S2 directly also you can use, and then from this A2 you will find out lambda 3 Q3. You cannot directly jump to Q3 or lambda 3. That's the point.
Okay.
Understood?
Okay. Yeah, yeah, yeah.
Okay, so anything else? See, there are many ways of performing these iterations, like subspace iterations, QR iterations, Lanczos iteration, and so on. In any finite element method, you are doing that course as well. So in finite element method, you will have eigenvalue analysis problem as well. In theory of vibration, you have it. Wherever you go, you will have it. And the solution, any software you use, Abacus, ANSYS, STAD, ETABS, the solution will be performed using either of these methods. One of these methods, and of course there are many other like Lanczos and subspace iteration and QR iterations and so on. So one of these methods will be used for solution of eigenvalue problem. So you should know what is happening behind the scene. So that's why this lecture and that's why this particular exercise. Maybe in one of the assignment you will have to solve these methods and find out eigenvalues and eigenvectors on your own. Okay. So if there are no doubts, then we can stop here.
Sir, one thing.
Yeah.
In the inverse power iteration, the error check we are doing is that we are doing in step number 2, where there we have a.
Yeah, let me go back there. Here, you see, there is easiest way is first you find out approximation to eigenvalue, isn't it? Now
Yes.
go to the next value of next eigenvalue approximation and see what is the difference. If the difference is very small, you can stop. So let us say first eigenvalue you obtained 10, next iteration you obtained, let us say 5, so difference is huge. Next iteration you found out 4, reducing. Next iteration you found out, let us say 4.1, very small difference. Next iteration you found out 4.003. Okay, now it is very small, so you can stop.
Okay, sir.
Got it? So you can stop based on eigenvalues as well. You need not always stop based on eigenvector. Eigenvalues are okay enough for stopping.
Okay, so basically we will be doing the error check in step 2 of every iteration.
Yeah,
Where we
in
have to-
every iteration you have to do the error checking.
Yeah. Okay.
Okay, anything else? Okay then, thank you.